Welcome to part 3 of week 2 of pre-calculus. We talk today about absolute value functions. Let me move to that topic. Well, first of all, as a function, absolute value of x is defined on the entire real line, and as you remember, absolute value of x is either x, in case when x is non-negative, or opposite of x, which is negative x if x is negative. That way, absolute value of x is always non-negative, and geometrically, absolute value of x simply measures the distance from 0 to the point on the real line that corresponds to x. Let me draw a point that corresponds to a negative number, say y. That distance will be absolute value y, which is negative y. And that distance is x, which is absolute value of x because x is to the right of 0. So again, geometrically, absolute value of x is the distance on the real line between 0 and the point which corresponds to x. Viewing absolute value of x as a piecewise defined function, we can easily draw the graph. It is, of course, y equals x when x is non-negative, and y equals negative x when x is negative. Note that the graph makes a sharp angle at the origin. By the way, what is the angle between these two lines, y equals x and y equals negative x? Because the slope of y equals x is 1, and the slope of y equals negative x is negative 1, the product of the slopes is negative 1, and as we learned last time, that implies that the angle between the two lines is 90 degrees. The lines are perpendicular. Lines y equals x and y equals negative x are perpendicular. They intersect at an angle of 90 degrees. All right. In this first example, we need to draw the graph of 2 times absolute value of x minus 3 plus 4. If you're familiar with the transformations of graphs, you can start with the graph of absolute value of x and apply necessary transformations, shift by 3 units to the right, vertically stretch by a factor of 2, and then move or shift upward by 4 units. If you're not familiar with transformations of graphs, we can solve this problem from scratch. All we need to do is just recall that if x is greater or equal than 3, we have f equal to 2 times x minus 3 plus 4, which is the straight line to x minus 6 plus 4, which is 2x minus 2. And if x is to the left of 3, our function can be expressed as 2 times 3 minus x, the opposite of x minus 3 plus 4, which is the straight line negative 2x plus 6 plus 4 plus 10. So if I draw the coordinate axis, and find the point, I perhaps don't need the graph below 0. In fact, I don't need the graph below 4, so I can save some space. The value of f at 3, by the way, is 4, so that's a special point, 3.4. And then to the right of 3, I have a straight line with slope 2. And to the left of 3, I have a straight line with slope negative 2. That will be the line y equals negative 2x plus 10. Altogether, this is the graph of the function 2 absolute value x minus 3 plus 4. This line is y equals 4, and this vertical line is x equals 3. All right. In example 17, we need to do the opposite process. We need to start with the graph of a function that was likely obtained from the graph of absolute value of x, and then write down the equation for that function. Well, we can immediately see that if x is greater or equal than 3, our function f is a straight line. That has slope 2, rise over run, rise is 2, run is 1, so slope is 2, and it passes through the point 3, negative 2. So we can use the point slope form for that and write that y minus negative 2 equals slope times x minus the x coordinate. So y plus 2 equals 2x minus 6, or in other words, y equals 2x minus 8. So to the right of 3, our function has equation f equals 2x minus 8. To the right of 3, we have a similar situation, except that now slope of that line is -2. As you increase in x by 1, you drop in value by 2. So that means slope here is -2. And if you again use the point slope form, you can write that y minus the y coordinate of the point, which is again -2, equals slope -2 times x minus 3. After some algebra, we get y plus 2 equals -2x plus 6, or y equals -2x plus 4. So if x is less or equal than 3, f equals -2x plus 4. Note that at the point at the value x3, the two expressions give the same value, namely 2 times 3 minus 8 is -2. And the same here, -2 times 3 is -6, plus 4 is -2. So we can write our answer as function f defined piecewise, 2x minus 8 if x is greater or equal than 3, and -2x plus 4 if x is less than 3. It's also worth noting that you can actually write this function using the absolute value form, because this is nothing but the graph of the function 2 times absolute value x minus 3 minus 2. You can easily check that. When x is greater or equal than 3, we have 2x minus 6 minus 2, which is 2x minus 8. And when x is less than 3, absolute value of x minus 3 will be 3 minus x. And you will get -2x, 6 minus 2 is plus 4. So you can have 2 times absolute value of x minus 3 minus 2 as your final answer in this example. Now I'd like to show you a number of examples of equations and inequalities involving absolute values. For instance, in example 18, we have the function absolute value of 2x minus 1 minus 3, and we need to find the x-intercept of that function. So we simply need to equate absolute value of 2x minus 1 minus 3 to 0. Of course, that means that absolute value of 2x minus 1 equals 3. That is equivalent to 2x minus 1 being equal to either 3 or -3. That is because absolute value is either itself or negative itself. I can write plus minus 2x minus 1 equals 3. Or I actually like thinking about this in a more geometric way, right? This means, by geometric meaning of absolute value, that 2x minus 1 is such a point on the real line. The distance from that point to 0 is 3, implying that that point is either 3 or -3. For these are the only 2 points on the real lines at distance 3 from the origin. So whatever way you prefer to think about absolute value, 2x minus 1 is plus minus 3, which means 2x equals either, if we have 3, it'll be 4, or if we have -3, we will have -2. So the two values where f is 0 are 2 and -1. The graph of this function, by the way, looks similar to the graph we had in the previous example. So the special point here is the point 1/2 -3, the vertex of the sharp angle, and the x-intercepts are at 2 and -1. That is the graph of absolute value 2x minus 1 minus 3. All right. Now example 19. What can we say about equation A? 2 plus absolute value of 3x minus 5 equals 1. When you move 2 to the other side, we have 3x minus 5 equals -1, which is less than 0, immediately implying this equation has no solutions because there is no expression whose absolute value is negative. Empty set, or you can write no solutions. For equation B, one equals 4 times x minus 2 absolute value minus 2. It's very similar to the previous example, example 18. If you move -2 to the other side, we have 4 times absolute value of x minus 2 equals 3. Now absolute value of x minus 2 equals 3/4. So x minus 2 either equals to 3/4 or it's equal to -3/4. In the first case, we have 2 minus 3/4. That is 5/4. Or here we have actually it is in this case where we get 2 minus 3/4. That's 5/4. In the first case, we get something else. We get 2 plus 3/4. That is 11/4. All right, that finishes example 19. Now, a couple of examples with inequalities involving absolute value. Say in example 20, we have the inequality absolute value of x minus 5 is less than 4. And again, thinking about this geometrically in terms of the real line helps. We are looking at all those x's that are at distance less than 4 from the point 0. There are only 2 points which are distance exactly 4 from 0. These are 4 and -4. And our interest is in those points which are closer to 0 than these two. So these are all numbers in between -4 and 4. So this inequality is equivalent to x minus 5 being between -4 and 4 strictly, and adding 5 to the sides of this double inequality, we get x is between 1 and 9. All right, and example 21 is only marginally more difficult. We have here the inequality -1/2 times the absolute value of 4x minus 5 plus 3 is less than 0. And moving 3 to the other side, we have -1/2 times absolute value of 4x minus 5 plus, is less than -3. And we mean here to multiply the inequality by -2. And remember, when you multiply an inequality by a negative number, you must flip the sign of the inequality. Multiplying by -2, we get absolute value of 4x minus 5 is greater than -3 times -2, which is 6. Again, we had to flip the sign. It's a common mistake to forget to do that. And again, thinking about this geometrically, we want all those points on the real line that are a distance greater than 6 from 0. There are exactly 2 points that are at distance 6 from 0, which are -6 and 6. We want those that are farther away than 6. So they're either to the left of -6 or to the right of +6. So our inequality is equivalent to either 4x minus 5 being greater than 6 or 4x minus 5 being less than 6. Maybe I should add a page and continue on the next page. Then, of course, this means that either 4x is greater than 11 or 4x is less than. This was supposed to be -6, of course. So 4x is less than 5 minus 6, which is -1. That is equivalent to either x being greater than 11 over 4 or x being less than -1 over 4, which you can write as the union of two sets. X belongs to the union of open intervals -∞, -1/4, union 11/4, infinity. And the theorem at the end of this simply generalizes all inequalities involving linear functions and absolute values. So whenever a is non-negative, the inequality absolute value of x is less or equal than a is equivalent to x being between a and negative a. Again, the easiest way to see why this is the case is to look at the real line. We want x to be a distance less than a, where a is non-negative from 0. The 2 points that are at distance a from 0 are a and negative a. We want x's that are at that distance or closer, so that's between negative a and a. And similarly, the inequality absolute value of x strictly greater than a is equivalent to either x being greater than a or x being less than negative a. Again, on the real line, here is 0. Here are points a and negative a, and we want all those x's that are farther away from 0 than is a. These are either to the right of a, so x is strictly greater than a, or union all those x's that are to the left of negative a, so x is less than negative a. All right, this finishes this topic. The next and last topic in week 2 is quadratic functions. We will do this later. Thank you.